Okay, hello, good day guys. This is the exclusive tutorial. So I'll be taking you guys current electricity 1, the first part of current electricity. So now this video is basically for Uniben and Delsu students. So you can make use of this video if you are a Uniben student, and you can also make use of it if you are a Delsu student. So now, what is current electricity? Or current electricity is simply defined in simple way the flow of charge particle and the flow of charge particles through a conductor is called current electricity. So normally, whenever current flows through a conductor, it moves from the positive end of the conductor to the negative end of the conductor. Whenever current flows, but when it moves from the negative end, first of all, to the positive end, take note, electron is the one flowing. So now, the electron drift velocity is the average velocity which a charged particle uses in driving through a conductor. So the velocity with which the charged particle, or rather the charged body, whether no matter the charged particle we are dealing with, flows through the conductor, the velocity which it uses is called the electron drift velocity. So now, I'll be talking about current and current density. So now, the quantity of charge present in okay, let me write this here. So now, the quantity of charge that flows through the quantity of charge body that flows through any conductor is equal to the number of charge, the electron flowing, the number of it, the electron itself flowing, and the volume with which it flows. So now, this volume, the volume is therefore equal to the area times length, or rather, but the length in this case is called the distance. Area times distance. So now, that distance is equal to the velocity times time. If you remember from our normal linear motion, that velocity is equal to distance over time. So now, the distance here is equal to velocity times time. So that is how I got this aspect of it. So now, the quantity of our charge, our dq, is therefore equal to NeAV dt. So now, the current flowing through any charge conductor is therefore equal to dq over dt. This is the formula for calculating current flowing through a conductor, and is equal to NeAV dt all over dt. So this dt can cancel out dt. So now, the formula for calculating current is NeAV. This is the formula for calculating current. Now, there's another quantity we call the current density. Now, the current density is the difference between the current and the current density is the fact that current flows through a conductor, like the whole part of the conductor is just flowing. It's just passing through the conductor, but the current density just flows through a particular point of it. Its measurement is precisely through a particular part of it. That is the current density. So now, the current density is usually calculated as the ratio of the current over the area. So now, if I imply this to my formula, we have NeAV all over the area. So the formula for current density is therefore NeV rather. So now, take note, our current density is a vector quantity, but our current is not a vector quantity. So that is that under that aspect. The next one I'll be talking of is the simple circuit. Our simple circuit is a very combination. Normally, every single appliances you have in your home is a simple circuit. Is a circuit. It can be complex, it can be simple, but any simple circuit, just a simple one, it's just a very combination of both internal resistance, external resistance, and the source of the EMF. So now, this is a diagram of a simple circuit. So now this is the diagram of a simple circuit. Now this circuit, the source of the EMF is embedded in it embedded in it is where you have your internal resistance. So now embedded in it is where you have your internal resistance. That internal resistance is normally subtracted from the major EMF. So you can get the potential difference, the potential difference flowing through the external resistor. So now a simple circuit is just a very combination of both the source of the EMF, the internal resistance, and the external resistance. So now the difference between potential difference and electromotive force, or our EMF, is the fact that the electromotive force is the work done of a charge flowing through the entire circuit, the one flowing through the entire circuit. But the amount of voltage, or rather flowing just through the external resistor, is called the potential difference. So it's called difference due to the fact that you are subtracting the external resistance from it. So now our potential difference is equal to our E minus the small v. This small v is called the one that has the voltage that carries the internal resistance. So now the V is equal to the big E minus small I r. So now our E is therefore equal to V plus I r. So our I small r rather. So our E is therefore equal to, take note, our V is equal to I r, our capital letter I r. So since our V is equal to IR, I can bring out my I, since I is common to both parts, giving me this. Then my I is therefore, or rather, my E is therefore equal to, the current can therefore be calculated as E all over big R plus small r. So this is what you get when constructing a simple circuit. This is the amount of what you can use in solving any question that has to do with simple circuit. Now the source of EMF, the source of the EMF is the one that produces the current that flows through this circuit. It is usually this device here. It can be a battery, actually. It can be a battery, it can be a generator, it can be anything. It's what is just generating the current that flows through the circuit. That is called the source of the EMF. So then the Ohms law was given by a particular scientist, where he said that the voltage is directly proportional to the current in any case. So now the voltage is therefore equal to IR. He said the voltage is directly proportional to the current, and also that the voltage is inversely proportional to the resistance. For me, I can make R the sort of formula having V over I here. If you divide here by I, divide here by I, you'll be having V over I. So now the voltage is directly proportional to, the voltage is directly proportional to the current, but for this place, the resistor is inversely proportional to the current here. So those were the two hypotheses the guy carried out. Then a resistance is the ability of a substance to oppose the flow of electron passing through it, while a resistor is a device that opposes the flow of current through it. Now resistance can be calculated to be equal to P L over A. This is the formula for calculating resistance, where this symbol means our resistivity. Then our L is the length of the conductor we are dealing with. Then the A is called the area. Take note, there are factors that affect resistance in a circuit. You can just use this formula to get the factors. The resistance is affected by the length, is directly proportional to the length. So an increase in the length of a conductor increases the resistance. Then is inversely proportional to the cross-sectional area rather. Then resistance also is grossly dependent on the nature of the material you are dealing with, and also resistance is also affected by temperature. The formula that shows that resistance is affected by temperature is this. So this is the formula that shows that resistance is being affected by temperature. Just like you know your qubit expansivity, your linear expansivity, and your superficial expansivity. So that formula that connects them, you can use it to connect both our resistance. So outside that fact, the resistivity also it also has a relationship that it exhibits with temperature, due to the fact that presence of impurity in a substance varies the value of the resistivity. So take note, this symbol is called, this symbol alpha here is called, for both cases is called the temperature coefficient. Now this arrow naught is the initial resistance we had, then the arrow final is the final resistance. Arrow the same thing with the resistivity here. So that is that under that part. Then I'll be talking about conductivity. I'll talking about conductivity. So just as resistance is the property of a material to oppose the flow of current through it, there is a property of a material that induces the flow of current through it. So that property is called the conductance of a material. Then the same thing with conductivity. Just as we have resistivity, we also have conductivity. And take note, resistivity and conductivity, they are like a constant for both resistance and conductance. So just as we have that formula that our resistance is equal to resistivity L over area. Take note, the 1 over resistance is equal to our conductance, is given as by this formula G. Then our conductivity 1 all over resistivity is equal to our conductivity. So that I can apply this into this formula here. If I take the inverse of this formula I gave here, it will now be 1 over R is equal to A over resistivity L. So from here, I can therefore continue by saying, introducing this guy for it. This guy is equal to this guy, so I've introduced it here. Same thing with this, A times, rather, 1 over resistivity times area over L. This is the same thing as what is here over the length. So I can just impute it. This is equal to resistivity. So now this is the formula that connects conductance and conductivity. So then the next one I'll be talking about now is circuits containing both resistance and capacitance, or rather that contains both a resistor and a capacitor rather. So that kind of circuit that usually contains a resistor and capacitor, they are just a special kind of a circuit, just like this simple circuit I drew. It contains resistance and capacitor. So what we are majorly going to be dealing in that part here is how it is being charged and how it is being uncharged. The value, the way voltage and the way its voltage varies when it is being charged and when it's being uncharged. So take note, whenever the circuit is being charged, the formula for it when you are charging it, in charging the circuit, the V is equal to So these are the two formulas here. Whenever it's being charged, the voltage is equal to the potential difference brackets 1 minus exponential minus t all over ROC. Same thing with when it is being uncharged, the circuit. So now there's one majorly asked question here. The question is that our time constant, or rather our time constant here, that's what it's being called. What is the value for it? The time constant is equal to the ROC. The value for time constant is equal to ROC. So normally our appliances we have at home, they they usually current usually flows through them, and when current flows through them, normally it generates heat, and that heat also has a power. It normally has a power. So now, say all these several devices we have at home, your home appliance, like your DVD, your speakers, and all those stuff, they generate it, and they are even usually built at a particular amount. They are usually built at a kilowatt hour. So now, let me quickly do a briefing on that. The power is calculated as current times voltage. For our home appliances, this is what I'm talking about now. The power is normally calculated as current times voltage. Then our P is also equal to current times the value for our voltage is equal to IR. So I can change this V to IR. We're having IR here. So it will now be equal to I square R. So P can also be equal to I square R. And P can also be equal to, since I can change I to be equal to V over R. If you divide both sides by R, you'll be having this. Then if I change I to be equal to V over R here, anywhere I see I will place this V over R times V. So we'll be having V square all over R. So these are the several formula for calculating power. And take note, 1 kilowatt hour is equal to 3.6 times 10 raised to power 3 joules, something like this. 10 raised to power 6 joules rather. So now for the last part, which I'll be explaining quickly, is measuring of current, voltage, and resistance. So now, in order for you to measure current, voltage, and resistance rather, if you want to measure the current in a circuit, you use an ammeter. If you measure the voltage, you use a voltmeter. Then the resistance, you use a ohm meter. So outside that part, in the ammeter and voltmeter, there's a special section of it called the galvanometer. So part of that galvanometer is where a deflection of current is usually being taken. So part of it is where deflection of current is usually being taken. And there's a device, whenever that your galvanometer reaches a full scales, that is when it is being deflected fully, it is called a full scale current sensitivity. That's what is being called. So now I'll be talking strictly on shunts, and I'll be talking strictly on shunt and multiplier. There are examples of devices that can either help you increase a DC current or reduce a DC current. Now, for the shunt, let's assume this is a device. This is the galvanometer in it. Initially, this current is trying to flow through it. Then this, the resistor, the shunt that I was talking about. Then the current of the shunt. Then this part is called the current of the galvanometer, the resistance of the galvanometer. So now, I didn't talk about series and parallel connection of current and of resistors. But I think since you are just trying to gain knowledge from this class, definitely you would have known how to calculate for a series and parallel connection of resistance. So now, seeing this circuit, this is called a shunt circuit. A shunt circuit. So now, for this circuit, since the shunt is normally being connected in parallel to the galvanometer itself, it is normally being connected in parallel to the galvanometer, and the galvanometer also has a resistance. Both of them have a resistance. Voltage is passing through this, voltage is passing through this. So now, in parallel connection, if you can remember, for voltage, for a circuit system, parallel connection of resistor, you find out that the currents passing through those systems is usually different, but the voltage passing through them is similar. So if the voltage passing through this guy and this guy is similar, so I can therefore say the voltage of the galvanometer is equal to the voltage of the resistor, that is the shunt itself, and the voltage is equal to IR now, I of galvanometer, resistance of galvanometer. Then same thing with the shunt bus, current of the resistor, voltage of the resistor. So now, this current value can be calculated from the fact that I said this current, whenever it's passing through a parallel connection, it will split. In parallel connection, take note, currents are different. They are different normally. So this initial current, when it's split, it will go here, giving this value for Ig is equal to Ig plus what? IR. So if you want to calculate the value for IR will therefore be equal to I minus Ig. So if you apply this to this part, you will now be having Ig Rog is equal to I minus Ig VR. So this is the formula you can use whenever you are given a question that involves them using a shunt circuit. But majorly why they use this stuff is that if you want to amplify the amount of what will I call it? You want to amplify current. You want to increase the value of current flowing through a resistor, or rather flowing through a galvanometer. You have to connect a shunt in parallel to it. In that way, you have increased the value of it, the current. That's what you are trying to increase. So that is that under that. Then the next one is the multiplier. A multiplier is a device simply that is used for measuring both current, voltage, resistor, anything. It can measure anything. That is what a multiplier is used. So normally, if you want to reduce the amount of if you want to reduce the value of current flowing through a particular galvanometer or a system, or rather, you have to connect a resistor in series with that device. So if you are connecting a resistor in series with that device, it will reduce the value of the current flowing through that galvanometer or the system. So in that case, the value for it will be equal to the major voltage passing through it will be equal to I bracket big arrow plus small arrow, where the big arrow is the radius of the multiplier. You take note, for this case you are introducing the multiplier. The multiplier is the device, is the resistor device we are talking about here. So now if you want to now calculate for the resistor, there it will now be V over I is equal to big arrow plus small arrow. Then our big arrow will be equal to V over I minus small arrow, taking this guy to the other part. You get? So if I take this guy to the other part, it will be giving me arrow, big arrow. This is the value for the resistance of the multiplier. Then this is the voltage through the passing through the circuit, the current, and the internal resistance. So that is how you calculate for that. So in the other video we'll be giving a calculation, the calculation aspect that has to do with current electricity. So if you have any question on this part I just ask on what I just taught now, or rather let me just give you guys, let me drop 2 questions that you can simply ask me in the WhatsApp group, and you can answer my question by sending it to the WhatsApp group. My first question is, you can write it down now as you are following this video. The first question is, what are the 4 factors that affect the resistance of a circuit? The 4 factors that affect the resistance of a circuit. Then, what is the function of a galvanometer? Then, what is the difference between the current and the current density? So I've given you 3 questions, so I'll be expecting that on our WhatsApp group. You can just go through the WhatsApp class, then those questions you can answer it for me and give me. So thank you for your time.
Learning online haven't been more fun. Exquisite Online Tutorials is a household name when it comes to academic excellence in online tutoring of 100 level students to 100 level students and college entrance examination candidates. With the power of artificial intelligence and human studies, Exquisite Online Tutorials have been able to interact with the intelligence of students worldwide, making the good ones better and even the better ones best. Just like Science Bob, Exquisite Tutorials has a great faculty of erudite tutors that inject knowledge, whether science or business management, to the cerebrum of her students. UTME lectures and other college entrance examination lectures are going on as well. Do you still need a physical tutor? No. Exquisite Tutorials got you. Please subscribe to our YouTube channel and follow us on Twitter and Facebook.